Hello everyone, welcome to Business Analytics Framework and Methods course. The purpose of this video is to go through the process of a specific homework question. The question is about how to implement the Adaline neuron or the Adaline perceptron model, and very specifically to illustrate the process of one loop of gradient descent and weight update. And here's a very important message. In this demo, I use an example data set. The example data set is also illustrated in the class. So when you attend the class, you will be working with the same example data set. I will use this example data set to illustrate the process of working through the Adaline model in one loop to implement the gradient descent and weight update. However, in your homework, you will be working with a different data set. The two data sets are about two entirely different cases. So you would have to adapt the codes and process that's illustrated here for the purpose of your homework. Otherwise, you will get completely wrong answers. And here's a little advice I would recommend. And in fact, I highly encourage you to attempt doing that homework question without first looking at this video, because this video is very detailed. It goes through the entire process and explains the details. By attempting the homework by yourself, you would have a very good opportunity to test your understanding of the process and to see if you have retained whatever you have learned from the lecture to implement and solve the problem by yourself. That will be the perfect learning method for you to best retain what you learned. If you have questions or trouble or need a little bit help in the process, be assured that you have this video to help you through the entire process. Okay, let's start. Before you start, make sure that you have downloaded this dataset, BZAN6357 default_1. It's a CSV file. Also, make sure that you have installed and correctly set up the Jupyter Notebook programming environment, launch the Jupyter Notebook, and create a new Jupyter Notebook. And now you should be ready to start. I will first import some important packages. Make sure you have installed them in Windows prompt. To be able to replicate the results that you see here, make sure that you run these two lines of codes and make sure that you don't change the numbers here. I use a NumPy random seed 1 and I use a random state 10. Run this cell. Takes a little bit of time and it's good. And just some very quick tip on how to use Jupyter Notebook very effectively. When you are working on the Jupyter Notebook, there are only two modes, the command mode and the editing mode. The command mode is when the highlighted cell shows blue on the side. The editing mode is when the highlighted cell shows green on the side and you have a cursor that is flashing somewhere inside the highlighted cell. Finally, to quickly switch between the command mode and editing mode, while you are in the editing mode, simply click Escape key. Now it has switched to command mode. And to quickly go into the editing mode for the current cell, simply hit the Enter key. Okay, move on. And just a reminder, you can run the cell regardless if you are in the editing mode or in the command mode. A shortcut to run the cell is by clicking Ctrl+Enter or Shift+Enter. Now I will run the cell to import the datasets. As indicated here, the dataset is BZAN6357 default_1. And the dataset is imported. I just hit Shift+Enter. I will do a quick sanity check, and it shows that this dataset has 1,000 rows, indicating 1,000 customers, and it has 22 columns. And of the 1,000 customers, 200 of them defaulted. Just a quick reminder, if you are not familiar with what are in the cases of this dataset and what are the columns, make sure that you carefully read the documentation file for this dataset. You can find and download them from Blackboard where you have downloaded this dataset. Let's take a quick overview of the data. I run this cell and everything looks okay. and to take a quick look at the descriptive statistic of the target and all the numeric input variables. I extracted the descriptive stat of these variables. I routed them to 2 decimal points and I transposed them. I transposed the result data frame, and what it does is it puts the variable names instead of as columns but as rows, so that I can show a long list of variables without having to scroll horizontally. And I only show mean, standard deviation, minimum, and maximum, and I have dropped the quartile statistics of these variables. As you can see here, the target variable has a mean of 0.2, which means 20% of the data set has a value of 1, 80% of the customers has a value of 0. A value of 1 for the target variable means that the customer has defaulted. Another important thing that you can notice is that for a large number of variables in this list, their range and the scale is very large. For instance, the set of paid variables has overall average means of in the 4,000, and their range can go up to even 380,000. Not the same thing for pay status, but the same case happened to the statement amount. This is the billing statement amount in a particular month. And also same thing for year birth. The year birth is in the 1900 range. So basically, a lot of these variables have large ranges. This is not a good thing for training a neural network model. To fix this potential concern, we would like to rescale all of these variables by standardizing the scale so that every variable except for the target variable will have a mean 0 and standard deviation of 1. So this is the data pre-processing step. To quickly rescale these variables, I will use the standard scaler from sklearn. It is convenient, it is effective, and it is robust. I will copy the codes here. And let me go through some of these codes very quickly. First, I need to select only those input variables that are of numeric type. And those numeric type variables include those that are integers and those that are floating number, which are decimals. And that is to say that I don't want to select those variables that are of object type or of string type. And also, almost never ever change or rescale the target variable. Next, I use the standard scaler, which I imported from sklearn. Standard scaler has a fit transform method. Will do two things in a row. It will first calculate the mean and standard deviation of every variable in this data frame, and next it will apply the standardization process by transforming every variable into mean 0 and standard deviation. Let me run this. Afterwards, it is a good idea to re-examine the descriptive stats again to make sure the rescale is successful. I use this line of code. The code is almost identical to the one that is run previously, but the data frame has been changed. Now the mean and standard deviation is all 0 and 1 respectively. Now let's start the process of implementing an Adaline model. In implementing the Adaline model, it is important that you understand how the process works and why do we code it as the way we code it. To better understand the process and also to help you, to guide you through the process and to know where you are now and what to do next, it is a good idea to have two things handy. One thing is the timeline picture that I made, which includes all of the critical steps as well as where a loop is. Where does it start, where does it end, and what's included inside a loop. There are two versions to the timeline. In one version, only critical steps and the timeline process is illustrated without any handwritten notes about how things are calculated. There is another version which includes my handwritings to illustrate how to specifically get each of the critical variables and steps. And I made these two versions for your convenience. You can feel free to use either version or both versions. And another thing to have it handy is a simple list of the critical steps inside each loop, as we will implement a complete loop here. Now let's begin the implementation. At the beginning, or even before beginning, you need to initialize some critical and useful variables and also control how the random outcome will turn out. You would like to be able to exactly replicate the results here to make sure that you're doing the things right. Here are the codes. Random state will determine the random draws and random randomization process, and The random state is the object to do that. Here, n is the number of observations or the number of rows in the data set. M is the number of numeric input columns or in the X data set that we will use. And keep in mind that this number 18, which is M, the 18 is the number of X variables. It is not exactly the same as the length of the weight vector, which is down here, weight owed. The length of the weight vector is 1 plus the number m, because there is one more bias term in the weight vector more than the number of variables that we use. Epoches is the number of runs, and for the time being we're not using this variable per se, so I picked a random number. Ada here is the learning rate, and it has to be quite small. Currently using 0.01. May not even be small enough, but it may be adequate. Later I will explain why this number has to be small. It's small because it helps speed up the learning process. And finally, I will print out some of the randomly generated number just to make sure that you get the exact same thing. You may compare the results here, especially these numbers, make sure that they are the same as the ones that you have output. After you have initialized the weights and other useful and critical variables, now let's begin the implementation. At the beginning, what you need is to prepare the data, both X and Y data. X is the same as the paired preprocessed X variables data frame, and Y is the pandas series object, which is only one column of the original data frame. And I do a quick sanity check to look at the columns names of the two data objects. The number of columns, the columns in the X data frame here is 18 variables, and there's only one variable in the Y series. I have also checked that the index of both X and Y match. This is critical because in the process we'll do some calculations that will rely on their matched indexes. Now we can start to implement those processes inside the loop, as you can see from the timeline. The first process in the loop is the decision process. Essentially, it is to calculate the net input function, which I use z as a variable name. We will implement the net input function. As you can see here, the net input function z is a linear combination of the w and x, including all the relevant input variables beginning from 1 to m and plus the bias term. To efficiently implement these calculations in Python, it's better to use the matrix calculation here. So to collapse these terms, to put it into matrix notation, these part here can be written as multiplication between the x matrix and the w weight vector. And to see that, imagine that the x matrix here is a matrix of n rows and m columns, which is n by m, because there are n observations or n rows of data, and there are m number of numeric input variables that we're using here. And this matrix can only be multiplied by another matrix that have to have m number of rows, and the weight vector is only a vector, so it only has one column. So the result of this multiplication will be n numbers of rows and only one column. And essentially, if you imagine that this input function denotes all the cases for all the observations, that goes from 1 to n. So z is a scalar that has a different value for all the cases. So the result of that is also a vector that matches the format or structure of this result. To implement this in Python, we use the numpy dot function. Essentially, the dot function is implementing an inner product process which matches up the last axis, which is m. The last axis m with the axis here. There's only one axis here. So it matches the m and m length of vector, and it calculates the inner product, which is the summation of the multiplication over each of the appropriate item of that. So here, for every row of the data in X, it takes one row of X and calculates the inner product between that row of x and that weight vector and stores it in the first element of the result. And it goes through all the rows of x to calculate all the members of that vector. And after calculating that, don't forget that there is a bias term. This bias term does not change across the rows. It takes the same value, so it simply is added to every row of that result. So in the end, the result of z will have a dimension of n. It's a vector. It has n elements. It's the same n as the number of cases in the data set. So here we will implement the first step of the decision process, which is to calculate the net input function z. And here is the code. See that this Python implementation is exactly the same as the gray notation that you saw previously. NumPy dot calculation, and there is a plus addition here. Run this. And to be on the safe side, print the first 9 elements of this matrix or this outcome vector, which is a vector, and compare your results to these 9 numbers. Make sure that they match exactly. And also, I talked about the length of the vector of this net input z. To verify that the length of z is the same as n, I will print out the dimension here. So I'll add a cell here, the dimension of z, by which I'll use a shape. So you can see here, it has 1,000 elements. 1,000 means there are 1,000 number of observations. It's important to note that even though in the implementation process, you are not required to calculate or to get the threshold function, as well as the classification errors of those cases by using the current weights, it is generally required, or it is recommended, that you know what these functions are, what role do they play here, how do they relate to the Adaline model, and how to understand them, and also be able to explain what they are. The next process here is to calculate the error, or the adaptive error. Now, because of the linear activation, error is not exactly the prediction error anymore. It is the adaptive version. That's why the model is called adaptive perceptron model, or Adaline. To get the adaptive error, you will first need to implement the activation function here. Now, the activation function for the Adaline model is a special case. It's a linear activation, which means essentially do nothing. However, we will not exactly do nothing here, because in other cases where the activation function is not linear, such as sigmoid or ReLU functions in either logistic regression or in neural networks that you will learn later, the activation function is not linear. So we will not skip this process, but here simply to implement the linear activation function. So I will use these codes. I will multiply z by 1, which essentially does nothing to the values of z, and assign it to a new variable, z act, which means it has been activated. Or another way to name that variable is you may use phi z, because the mathematical symbol for the activation function is phi. Okay, I will run this, and then let's just check the values of this array. And z act has the same dimension as z, which is a vector. Values should not change at all. You should get the exact same values as before. After that, you will be ready to calculate the adaptive error. Here is how to calculate adaptive error. After linear activation here that you have implemented, the adaptive error is calculated by subtracting activated input function, the z act or phi, from the y vector. Both of these two are a vector of length n, so both of them are n by 1. The result will be another factor of n by 1. It is quite straightforward. We will implement that subtraction here. We will quickly check the first 9 numbers here. The next step of the process is the optimization process. It is quite important here. It implements both gradient descent, or that you will calculate gradient function, and then you will calculate delta weight in order to update the weight vector here. Now, I should also note that even though you are not required to calculate the cost function here, it's always a good idea to know what it is. Cost function, also sometimes referred to as a loss function, is a function that optimization process is trying to minimize in order to get the optimal weights. And the gradient function is derived from the cost function. So it's always a good idea to know that. Here is to understand how to calculate gradient function. The gradient function is needed because you need to calculate the delta weight, weight vector update. You will use the gradient function as part of that calculation. The gradient function, as using the notation here, the upside down triangle, J with respect to a specific weight parameter here, is calculated by using the values of the y and activated input function, which is essentially error. This part will reduce to error, as you can see here, multiplied by x of a particular particular row of the data. And as you know that here x includes all the variables in the x matrix, so it's a matrix, and in the matrix notation we would have to transpose that in order to multiply with the error vector, and I'll explain why. But also pay attention to the negative sign here, because it's a sign that is a part of the gradient function. Don't mess up with the negative. Don't skip it or don't leave it out. Otherwise, you will get a process that will be working in the other direction of your optimization. To understand the matrix notation of this formula, you would first be sure to understand that the structure of, or the shape of, gradient function. The shape of the gradient function is the same as the part of your weight vector that corresponds to the x variables. So gradient function in the end should be a vector of length m, which corresponds to the number of input variable columns. And because it's a vector of that length, then you would need to multiply a matrix that has m number of rows. Because the X matrix originally has n number of rows as the observations and m number of columns as the number of variables. So you would need to transpose that in order to get the right result. And doing that will match up perfectly with the dimension of the error vector, which has n number of rows, records the adaptive error of each cases in predicting the outcome. So the result of doing that, here we're basically switching the places and we're transposing X matrix in order to put it into matrix notation. So X transpose will have the format of n by n times error vector, which has a shape of n by 1. And the result will be m by 1 vector, which is the same structure of the gradient that we need. Now to implement that, we translate that into Python codes, retain the negative sign. Now doing the matrix multiplication, we can use the numpy dot implements the inner product of between every row of this transpose X with the entire vector of the error. So each row of X transpose will have n elements. The error vector has n elements, so they will match, and it will calculate the inner product and put it in the first element of the output vector, and it iterates throughout the rows of the X transpose, and the result will be a vector of length n. Coming back to our codes, I will implement gradient descent. So here the Python codes will match with the notations earlier, and I will run this. Make sure to print out 9 numbers of them and make sure you have the exact same number. And the next step of this process would be to calculate delta weight, the amount of shift to adjust the current weight, the notations, and the formula. Now the best way to implement delta weight is to go through 2 steps because of the slight difference between the bias term and the rest of the weight terms. The bias term is stored as the first element, and all the other weights are stored beginning with the index of 1. We first calculate those part of the weight vector that corresponds to the X variable, which is those elements beginning with the index of 1 to all the way to the end. Now the formula to do that is to multiply the negative sign, eta, the learning rate, and the gradient function that you just calculated. And to implement this code in Python, we would simply multiply the negative sign, another negative sign, eta, which is a scalar, which means it's a simple number, and the gradient vector, which has length m. The result will be a vector of length m, and to store it to the delta w vector. And keep in mind that delta w vector has the same length as the w vector, so that's why this formula will calculate only those m elements beginning the index of 1 all the way to the end that corresponds to m elements of the weight vector. Why? The Ada learning rate has to be quite small, and let me illustrate that. Recall that you have calculated the gradient, and in order to calculate the weight update, or delta W, which I just talked about and showed you the formula, you see that delta weight is calculated by multiplying Ada, the learning rate, with the gradient. And take a look at these numbers of the gradient. It is quite large. Even though we started with very small data, the data points after rescaling becomes quite small, and we started out with weights very small, very close to 0. And look at the gradient. To briefly say a thing about gradient. Gradient is the slope, is the derivative of the cost function convex curve. So it seems like the slope is very steep. If we don't have a small enough learning rate, we will end up correcting the weight too much and end up with a weight that's even worse. So in a way, if we don't have a small enough learning rate, we will be hurting our weight instead of improving our weight vector. So that is a nutshell of explaining why the learning rate has to be small enough. Now, to talk about the second step of weight update, delta W, we know that the bias term is not associated with any x data, or it can be thought of as associated with a vector of 1 that has the same length as the x matrix. It's a vector of 1 of length of n. So in that sense, we are effectively multiplying a vector of 1 with the error vector. And in matrix notation, multiplying the two vectors essentially means to calculate the inner product of the two vectors. So it's almost equivalent to calculating the sum of all the elements of the error vector. So there you go. Translate that into Python codes. It's essentially multiplying all the elements here. We have two negative signs, so essentially they cancel out. So what we left with is an Ada scalar times the summation of all the elements of the error vector, by which we use the dot sum method of the Python series. Coming back to our codes, to calculate delta weight or weight update, I will use these codes. It's a two-step process, as I talked about. Those m elements beginning with index 1 is updated by multiplying minus Ada and the gradient, whereas to the delta W for the bias term is only using the summation of the error vector and times the Ada. And also know that the two minus sign have canceled out. Now I'll run this and print out all the values of delta W. Now why do I print all the values? Because this is not a very long vector. It's not a vector of length n, but it's a vector of length m plus 1. It's the update portion of the weight vector, and the weight vector is not so long, so we can compare these values with the original values that we have previously. And the final step in this process within the loop will be to update the weight by using the delta weight that we just calculated. So the weight update step is straightforward. We add the delta weight to the original weight, it becomes the new weight. In Python implementation, I would like to clearly show the difference between the two weight vectors here is to spell out their nature. I have the old weight vector, I have the delta weight, so I add them all together, it becomes new weight vector. And after that, don't forget to replace the old vector with the new vector, because now the old vector has been updated as well. The length of these weight vectors are all m plus 1, as you know. Now going back to our codes, we will update the weight vectors, and I will use these codes. I will first create a new vector, which is weight new, by using the old weight vector and the delta weight. And before I update or replace the old weight vector, I need to print them out, otherwise I will lose them. So after I print them out, I replace the old weight vector, and it reflects an update process. Now running this code, I have put the old weight before replacement and the new weight by incorporating the weight adjustment adjustment or delta weight, and you can compare and see how much the weight have changed in just one implementation, and I'm quite confident that by updating these weight, the prediction error has dramatically reduced. Now I will illustrate that in the class as well as in other videos. Now here we have completely implemented one loop of the Adaline model, beginning from preparing the data all the way up until the end of the first loop. Now, the next step would be to construct the for loop in order to implement multiple epochs or iterations of the loop to continuously optimize and improve the weights. Now, those will be the content of another video or another question of the homework. I certainly hope that by this time you have a much better understanding of the process of at least one loop of optimizing the weights in the case of the Adaline model, and I hope you have enjoyed this video. I hope this video has clearly explained the steps of implementing at least one loop of the Adaline model. If you still have any questions, be sure to email me or let me know, or we can have a virtual meeting, or we can solve things out in emails or in other means of communication. Be sure to let me know. See you next time.